Now the next type is histogram equalization. Now in histogram equalization, similar, if you want to increase the dynamic range, either you can go for histogram stretching. It is very easy method to actually stretch the histogram or to extend the dynamic range. But one more type that you can actually, this is the most powerful type if you want to distribute the histogram of the input image equally around or all over through the dynamic range, that is zeros like L minus 1. Okay, so this is a histogram. This is PR of R. Now the intensity levels in the image may be viewed as random variables in the interval 0 and L minus 1. Okay, intensity levels are from 0 to L minus 1. These are nothing but the gray level. Let P suffix R of R and P suffix S of S denotes probability density function, that is PDF. Probability density function. So the entire range will be considered as which start from 0 to L minus 1. Or it is, if it is not 0 or L minus 1, you need to make to 0 to L minus 1 or whatever after equalization. When you distribute equally the histogram or gray levels or number of pixel all over the area. Now you're considering the A image arbitrary PDF, that is this, the actual histogram you will find like this, like it does not contain the uniform shape. It is increasing, downgrading, increasing, decreasing, increasing, decreasing. Okay, this is nothing but the uniform, you can say uniform. So actual our desired output should be the uniform one, but you will not get exactly the uniform output after processing or after doing the histogram equalization on uneven part of your histogram. But the aim is to make it as nearer to the uniform. Okay. And now if you consider the value for this at S, it is nothing but the slope 1 upon L minus 1. What is the slope formula? Y2 minus y1 upon x2 minus x1. You have x2, x1, x2 and x0. Suppose if you have x2 minus x1, x1 is 0, x2 is L minus 1, y2 is 1. Suppose this is 1 and this is 0. 1 minus 0 divided by L minus 1 minus 0 will be 1 upon L minus 1. That will be the slope L minus 1 for the uniform, you can say, or for the one value. When the output value is 1, here L minus 1 will be the maximum input value. Now this should be the effect of histogram equalization. The result of applying transformation in this to all intensity levels are the resulting intensity S, that is output intensity S, have the uniform PDF independently of the form of PDF of R's. Okay, so the aim is to make the histogram uniformly distributed over the range of 0 to L minus 1. That is probability density function. That is the area. That is the density of histogram. This is also the density of a histogram. That is the area that you cover. Now in histogram equalization, you have two types or the multiple types of functions. Like suppose you have this and this. This is strictly one single value. If you are giving single value, you are getting single at the output. If you are giving single value at the input, you are getting single. But in many function, you are giving multiple times the input value, multiple values at the input, but you are getting only single value at the output. Okay, so it has monotonically increasing function showing how multiple values can map to a single value. This is, it is increasing, 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 then stable for multiple value, because it is stable for the one value, that is single value SQ. Again it is increasing, 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 increasing. So monotonically increasing as well as it has some stable value, that is a plot. You may have only the strictly monotonically increasing. Strictly means if you're giving anything in the input, it will have the different value at the output. For particular gray level, it will have a different output level. For particular gray level, it will have the different output level. That is known as strictly monotonically. It is not strictly monotonically. It is monotonically for up to this extent. Then it will give the single value for this multiple value, and then it is going again for the monotonically increasing. Now, if you consider the output image S is nothing but the transformation on R, which has the value, that is gray level value 0 to L minus 1. 0 to L minus 1. Now, the transformation R is strictly monotonically increasing function in an interval gray level 0 to L minus 1. Yes. When 0 and transformation R is also 0 to L minus 1, or for 0 to 0, the R should be greater than or equal to 0 and less than or equal to L minus 1. These are the conditions. Okay, same thing has been written. Okay, now if your transformation R is continuous and differentiable, what it will be? If it is continuous, we need to consider the power density function PDF and cumulative density function. Now, in order to consider that, you're considering this power density function for S and power density function for R for the area ds, differential area R, or differential area of R over the area R and over the differential area S. So power density function for S and power density function R should be equivalent in order to equalize the condition. From that, so P suffix x S of S can be written as P suffix R dr by ds. If you take this ds here, dr by ds, so you have the formula dr by ds is nothing but PSS divided by PRR. Okay. Okay. This is a general power density. This is a representation of your PDF power density function. So power density function, it has a value from 0 to your input value R, that is the gray level value, and you have the power density function for the gray level PR, W and del W over the area W. This is the standard power density function for the given input image. Now for L minus 1, you can go for without L minus 1. You can consider, you can derive without L minus 1. If there is a L minus 1, if you are considering L minus 1 value, if you're considering the L minus 1 as a 1, you can write the same equation without L minus 1. So it will be 1. So 1 will be, you don't have to write a 1 specifically. So either you can go for L minus 1 or nothing. If I'm considering L minus 1, so that will be the power density function with L minus 1. Okay, so L minus 1 integration from 0 to R PR of W and del W. Now I will differentiate this S with respect to R, that is differentiating S with respect to R, that is d by dr of S, differentiating S with respect to R, so that will be differentiating T of R with respect to R. Okay, so that will be the L minus 1 d by dr, again both the side you are taking differentiation, and 0 R PR W del W, same thing. Now the power density function, that is the integration of PRR, is nothing but this. You are just replacing the input value to the W. This is the differentiation of your power density function. So PR of R. If you are considering L minus 1, then you need to consider this L minus 1 as it is PR of R, as P suffix R R. If you are considering 1, only PR of R. You don't have to write L minus 1 here. You don't have to write L minus 1 here, L minus 1 here. Simply this integration and this differentiation with integration and PR of R. So you know you have now ds by dr as L minus 1 PR of R. Okay. So you have ds by dr as L minus 1 PR of R. So I can replace, you have ds by dr. Okay. ds by dr. So if you consider ds by dr, ds by dr is equivalent to PR of R divided by PS of S. Okay. Same thing. You have same equation PS of S. Now make this ds to be here in this side. So PR of R dr by ds. So dr by ds, but you got ds by dr. You got ds by dr. That is L minus 1 into PR of R. So this is a reciprocal of dr by ds. Yani ulta. So you will consider same PR of R. PR of R dr. PR of R dr. And ds यहाँ पे हो गया. So ds by dr will be the reciprocal of 1 upon L minus 1 PR of R. PR of R cancel. Okay. PR of R, L minus 1 PR of R cancel, and you will be with 1 upon L minus 1. So that will be the uniform density function. Uniform density function 1 upon L minus 1. ये वाला 1 upon L minus 1. अगर यहाँ पे L minus 1 नहीं है, then it will be only 1. PR of R divided by PR of R, that is cancel will be 1. This is the actual technique to equalize the histogram. Now this is the input image, that is it has poor contrast, or you can say very low contrast image. The histogram is situated only for this range. That is why the image is poor. Okay. Then if you distribute this histogram from for the range 0 to L minus 1, then you will be able to see the image very clearer than the original one input image. Okay, this is result of histogram, means after equalization of this histogram, now the histogram is having the range from 0 to like L minus 1, and that is why you have the pixel values for each and every gray level, means you have the detail about each and every gray level of 255 image, that is L minus 1, that is gray level image. Now for the continuous case we have studied this. Now what will be about the discrete values? Same formula, only अब integration के अलावा यहाँ पे आएगा, that is the summation, and you are considering 0 से लेके k is nothing but the gray level value. Okay, means you are actually considering the PDF value, or the summation of PDF value. I will show you. So the continuous case, for the continuous case integration, and for the discrete value you will take the summation, same thing, same equation, only the difference is summation and the integration. For example, if you are considering a 3 bits image, a 3 bits per pixel image, L will be 8. If L will be 8, suppose that 3 bit image L is equal to 8 of size 64 by 64. So total number of size means 64 by 64 का image है. 64 vertical, 64 horizontal, m into n will be 4096. So total number of pixels are 4096. Okay, and 0 repeats 790 times, 1 repeats 1023 times, 2 repeats 850 times, 3 repeats 656 times. This is nothing but the number of pixel for the gray level value 0 to like 7. And then you have normalized that normalized histogram, means you need to divide 790 by total number of pixel, that is 4096. You will get 0.19. For 1023 divided by 4096, that is total number of pixel, you will get 0.25. That is a normalized version or normalized histogram. Okay. Now the formula is we have studied already. For the discrete value, the formula is L minus 1. If you consider 3-bit pixel, what will be the L minus 1? 7. Because 3 bits per pixel, 2 raised to 3. You need to multiply 2 thrice. 2 into 2, 4. 4 into 2, 8. 8 is equal to L. So L minus 1 will be 7. So 7 and summation. Okay. So 7. First, we need to consider the first for for the pixel value 0. So that is why S0 T for R0, the transformation on R0, L minus 1 that is a 7, 0 to L minus 1. यहाँ पे एक ही है that is 0.19. So 0.19 into 7 will be 1.33, which is equivalent to the 1. Now you have a 1 level. The gray level value will be 1. Now for 1. Now for 1, you have L minus 1, and now you have 0 से लेके 1, that is 0 से लेके 1. 0 से लेके 1, 0 से लेके 1 means 0.19 plus 0.25 and multiply by 7, that will be 3.08 will be 3 S2. Now the what will be the summation? Summation will be 0 1 2. So you will have j from 0 से लेके 2 for second pixel, sorry, for the gray level value 2. So you have 7 multiplied by 0.19 plus 0.25 plus 0.21 will be 5.67 will be 6. Similarly, you will find up to 0 S7, that is 7. So these are the new output gray levels after doing your PDF and CDF, that is cumulative density function. It represents the accumulation. You need to accumulate these values. So add 7 gray level, you need to add all these, okay, from 0 to 7. This is one of the method to solve to get the new values. After rounding up and rounding down, you will get the new values. And another method that we can solve, you will form a table which will have the gray level value 0 to 7, then number of pixel, and then total number of pixel 4096. Then PDF, you have a PDF. The formula for the PDF is nothing but the normalization, that is probability of occurrence. 790 divided by 4096 will be 0.19. 1023 divided by 4096 will be 0.25. 850 divided by 4096 will be 0.21. Then you have a cumulative density function CDF, that is 0.19. यहाँ पे कुछ भी नहीं है, तो 0 plus 0.19 will be 0.19. Then 25, 0.25 के लिए CDF will be 0.19 plus 0.25 will be 0.44. Then for 0.21 के लिए 0.44 plus 0.21 is equal to 0.65. For this value, 0.16 plus 0.65 will be 0.81. Similarly, for this value, 0.81 plus 0.08 will be 0.89. Up to this, you will be with 1, that is 0.98 plus 0.98 plus 0.02 will be 1. So you have now CDF now, and you need to multiply your CDF with L minus 1, that is 7, multiply by CDF. 0.19 into 7 will be 1.30, that is 1, 3.03, 5, 6, 6, 7, 7. So you have three gray value, that is 5, 6, 7, which is in the level 7, gray level 7. Means you need to uh, the repetition of this pixel, 245 plus 122 plus 81, you will represent at a gray level value 7. There is a new modified version after equalization. Okay, so you have a the new values 0. यहाँ पे एक भी 0 नहीं है, तो 0 repeats 0 times. पहले था 0, 0 was repeating 790. The 0 was having 790 pixels in the image. Now after equalization, 0 has nothing. Now 1 has 790, 3 has 1023, 0 nothing, 1 के लिए 790, and after 1 2, there is no new value 2, so 2 will be 0, 3, 1023, 4 भी नहीं है, 4 is absent, so 4 will be having no pixel, 5, 850. Now 6 is the combination of 3 and 4. 6 is a combination of 3 and 4, and 3 and 4 has a repetition to 656 and 329. So 656 plus 329. For the 7 new gray level, 245 plus 122 plus 81, 245 122 plus 81, and you will draw the histogram like this. Okay, so starting में ऐसे ही था, after equalization now you can say it is a uniformly distributed after applying the transformation function, that is the transformation on this. So this is the A is the original histogram. So before this the histogram was like that. After using a transformation function, that is PDF CDF, multiply the CDF with the L minus 1, okay, you will get the uniformly distributed function. So this is the histogram equalization. So you have original histogram, transformation function, and equalized histogram. Okay, left column represents the image, center column corresponding histogram, equalized image, and right column histogram of image in the center column. Okay, so left columns are nothing but poorly contrast or inferior quality of an image after uh, quality has been upgraded up to after histogram equalization. You have the new version of your image. This is the center column for the new equalized histogram, and this is the histogram of equalized image. So after using your histogram equalization, you will get the suitable image, or you can say the image will be more suitable for the application. It will be more uh, good than your existing one. And then histogram matching. This was histogram equalization. After histogram stitching, we have studied histogram equalization, and this is the last of histogram matching. In this histogram matching, you will be given with your specified histogram, means the predefined histogram. So in the examination they will tell you, or they can ask you, please match your histogram A, that is your input histogram, with the given histogram B. Means your histogram should be look like the given histogram or a specified one. Means what? For example, if we have the histogram PR of R, we have the histogram that is a power density function. This is the specified one. So PRR and PZZ denote the continuous probability density functions of variable R and Z, and P suffix Z of Z is the specified probability density function. Means you need to match the probability density function PR of R with PZ of Z. Means PR of R should be look like PZ of Z. Same again, how you write the PDF, that is S is equal to transformation on L minus 1 0 से लेके R 0 to R P suffix R W del W. Similarly, I will denote the new function Z of Z, that is T of R जैसे था वैसे ट्रांसफॉर्मेशन T on R था, यहाँ पे ट्रांसफॉर्मेशन G on Z रहेगा. So L minus 1 सेम 0 से R था, 0 से Z रहेगा, P Z रहेगा, because R था तो यहाँ पे Z रहेगा. I will consider a new parameters T and del T, and it should be look like S, means S should be look like this. So T of R should be look like Z of Z. Okay, so that is nothing but Z will be G inverse of T of R. अगर G को यहाँ पे G को यहाँ पे लिया तो it will be the reciprocal, that is G inverse like this SR. ऐसे सेम है ये equation. So ZZ should be look like g of z, that is transformation g on z, should be equal to transformation on r. When I take g from this side to this side, that will be g inverse, g inverse, that is s, and this g inverse of transformation on r inverse. Then obtain p suffix r from the input image, and then obtain value. Means you need to equalize the first histogram, that is the given histogram, input histogram, and then you will equalize the specified one histogram. And from the specification, if you will be able to match the value, means you are able to match the new output value after equalization of the specified one, then you will write all the number of pixel in inverse direction. Means you will match your all the pixel or the repetition or the pixel value of s to the gray level value of z. Okay, this is the example, same example we are taking. You have the gray level, number of pixel, normalized version, and the specified one, that is z0, 0 kilo 0, 1 kilo 0, 2 kilo 0. There is no any number of pixel for 0 1 2. It is starting from 3 4 5 6 7. So you need to consider 3 4 5 6 7, and you need to first equalize the histogram. You have to equalize both the histogram first. So we'll proceed. So this is yeah, and after equalization, we had found that s0 is 1 3 5 6 7 7 7, from 4 5 6 7. uh, so you have a new value after histogram equalization. I think this is wrong. S46. Okay, what it be? So you need to equalize the histogram. So after equalization, for this histogram, you will get the new values. S0 1 0 missing tha, 2 missing tha, directly S1 will be 3. 1 3 5 6 6 triple 7. 1 3 5 6 6 triple 7. S0 1 था, S1 3 था, S2 5 था, S3 6 था, S4 was 6, S5 was 7, S6 was 7, S7 was 7. Okay, if you're considering this, so you will get the new values of gray level after equalization. Same we had done already. And then you will again equalize the new histogram, and again you will get the new level. 0, anything multiplied by 0 will be 0, 0 will be 0. For these three gray level you will get 0 1 2 के लिए gray level 0 ही रहेगा. Now after z3 you have 1.05, that is approx value will be 1. Now z4, 2.45. In some book they have taken 2, in some book they are considering 3. If we consider this is at 3, and uh, okay, then you have new levels after equalization of new specified histogram. 0115, 0119, 0.15 था, and sorry, 0.19. Okay, 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 okay. Hmm. First you will equalize this new histogram, that is specified one. equalization of this, you will get the new values, and you will get the new values for the specified one, that is ranging from 0 के लिए 0, 1 के लिए 0, for gray level 2 is 0, then for gray level 3 is 1, for gray level 4 is 3, for gray level 5 is 5, gray level 6 is 6, and gray level 7 is 7. And then you will distribute your histogram. How? Now um, in this, the new modified one, G1 gives nothing, G2 gives, or Z2, that is 2 gray level in the Z that is specified, gives nothing, 0, and then Z0, that is 0 gray level, gives nothing in the specified one, 0. So 3 values or 3 gray level value has nothing. Now you are starting from your Z3. After Z3, that is when you hit the gray level 3 in the specified one, you will get the value 1. Okay, and we have the value as 0 as a 1 in the old one, जो अपना पुराना input image है उसका. Similarly Z4, you have the value S1, so you can accommodate your S1 value. S1 value क्या था? That is S1, 790. 790 is nothing but 0.19. 790 or CDF or 790 0.19. Okay, so you have S0, S1 level, because S1 1 के लिए 3 आउटपुट हो गया था, 0 के लिए न्यू वैल्यू, यानी 0 ग्रे लेवल है तो न्यू ग्रे लेवल 1 हो गया था, जब 1 था तो 3 था, 2 था तब 5 था, 3 था तब 6 था, 4 था तब 7 था, सॉरी यहाँ पे 6 था एक्चुअली. तो अगर यहाँ पे S4 एंड S6 है तो इट शुड बी ओके, 2 values. Now it is a perfect one. Okay, so you will write the value of your S0, S1, S2, S3 and S4 and S5, S6, S7. That is the value of old one. Old one. 0.19, 0.25, 0.21, 0.24 and 0.11 in this. The combination of gray level 5, 6, 7. 5, 6, 7 यानी 7 पे जो हम लोग ने किया था, that is 0.6 plus 0.3, 0.09 plus 2, that is 11. So 0.11, 0.11. Like this, we will match the histogram. Okay, means it will be, so it will look like this, which will start from your 3, 4, 5, 6, 7. Okay, which will start from your 3, 4, 5, 6, 7. You will distribute your this function as like this. So 0.19, okay, 0.25 for 4, for the gray level 4, 0.21, and then the remaining 0.24 and 0.11, because you have 3, 0.6 plus 3 plus 2, that is 11. 0.11 will be at level 7, because you have S5, S6 and S7 which are having the value 7. मीन्स जो 7 है, जो आफ्टर इक्वलाइजेशन ऑफ योर ओल्ड हिस्टोग्राम 5 6 7, that is 5 6 7 are containing the total number of pixel. ये तीन, ये वाले तीन, ये वाले तीन, तो 0.06 plus 0.03 plus 0.02, total 0.11 will be at 7 बराबर. देन आपके दो है, 6 और 6 वाले, जीरो S3 and S4, the gray level 3 and gray level 4, gray level 3 and 4, 0.16 plus 0.08, so 0.24, टोटल दो. 0.24 आपके आएंगे 6 पे, जैसे ये S3 and S4 आपके आएंगे 6 पे, ये तीन आएंगे आपके 7 पे, Z7 again. This is my mistake while preparing a PPT. Okay, wait a second. This is 7. Okay, if I extend this. Okay, now this is proper one. Now your entire data is correct. You will not have any doubt now. So by matching this your modified equalized version of your input histogram with a specified one, you will be able to plot a histogram of your input image to the specified one. Now you can watch this video repeatedly so that you will not have any confusion for the histogram matching. Other than your histogram equalization and histogram stretching, it is a complicated one. It is not that much complicated. You need to match, you need to consider the, you need to match your input values, that is S values, in inverse direction. You need to think in an inverse direction. Okay, that is G inverse of transformation on R. That will be the modified Z. Okay. Same histogram matching 1 3 5 6 7 was actually the after equalization. After equalization of your input image, you were getting 1 3 5 6 7, जिसमें 0 के पिक्सल थे 1 में, 1 के पिक्सल थे 3 में, 2 ग्रे लेवल के पिक्सल थे 5 में, 3 लेवल के ग्रे पिक्सल थे 6 में, एंड 4 के एक्चुअली ऊपर थे 6 में. ओके. एंड देन ऐसे. ओके, 4 के पिक्सल लेवल 6 में थे एंड 5 6 7 के पिक्सल 7 में थे. ओके. And after the equalization of your Z, you have a new input value, that is 3 5 6 7, जो भी जो पहले भी 3 4 5 6 7 ही थे. And so you will map the number of pixel of the original one to the specified one. Okay, then you will map the number of pixel 3 to 4, number of pixel of 5 to 5, means equalized version of your histogram. Then number of pixel of 6 and number of total number of 6 pixel, that is 0 point जो था ना 5 6 7, 0.6 0.03 0.06 0.03 0.02, like this. 0.06 0.03 0. यानी 5 6 7 5 6 7 के, ये यहाँ पे 5 6 7 के इन 7 तो 7 ही है, 6 का 6 ही है, 5 का 5 है, 3 का 4 हो गया है, 1 का 3 हो गया है. So you will have the final histogram which will match with the specified one. That is nothing but the histogram matching. This is the image of a moon. Okay, and this is the original image. That is poor contrast, you can say. It has only near to the zero value, and this is a transformation function, equalization function. After equalization, uh, histogram. Now the image is not that much clear in this presentation, but it will be better than here the original one. Okay, the transformation function for histogram equalization. This is a transformation, that is t of transformation on r, t of r, and then the histogram equalized image. Yeah, after equalization you will be having the very much pure, or you can say the better than your input one. And then this is the histogram of your equalized image. Now you have a specified, a figure shows the specified histogram. You have a specified, the specification should be like this only. Now you have a transformation B, and then you have the enhanced image using mapping from the curve to enhance image. That is the enhancement after doing some transformation. This curve 2, the number 2. Okay, this is the image, and the histogram of C means you have specified, means you had matched this equalized version of a histogram with this histogram, and then you have written this, okay, which is equivalent to the specified one, which is equivalent to the specified one. Okay, so this is histogram matching. Thank you. Thanks a lot.